We will now move on to section 4.4.4 on the binomial theorem. On the face of it, I think this is perhaps the most challenging part of the CLEP exam. It requires using factorials and binomial coefficients to make statements about polynomials. However, it is also very beautiful, so I hope you enjoy this section as much as I do. We can use the binomial coefficient to discuss, well, binomials, things like this. So for example, x plus 1 squared. In this case, n would be equal to 2 and y would be equal to 1. But we can think of these all as variables if we like. The question this tells us is how to expand this. Now the formula is a bit complicated. It says that it expands to be something like a given power of x, a given power of y, but then the coefficient on them is given by this binomial coefficient. Hence the name. So to see why this is useful, let's just look at a couple examples. X plus 1 squared we can do rather easily and get x squared plus 2x plus 1. How about x plus 1 to the 10th? I think you would be here for an awful long time if you tried to expand this out directly. So that is what this result is aimed for. It's aiming to address complicated polynomials like this and to try to expand them in a simple way. So let's look at an example of this at x minus y to the 5th. Again, if I tried to sit there by hand and crank this out, I think I'd be here for an awful long time. So we'll try to use the formula. So I take my sum from k equals 0 to 5 because n is equal to 5. And what are my terms? I have x to the k minus y, because the theorem was stated with a plus there, so n minus k. And then I multiply by the binomial coefficient n choose k. So writing this all out, I get something like x to the 0 minus y to the 5th and choose 0. X squared minus y cubed and choose 2. And we're getting closer and closer. I know that n is 5, so I can go and replace these all with 5 if you wish. And now it's a matter of just simplifying everything. X to the 0 is 1, minus y to the 5th is minus y to the 5th like this. 5 choose 0 we would see to be 1. Then we would get plus xy to the 4th times 5 from that binomial coefficient minus x squared y cubed times that binomial coefficient would be 10. Then right, and plus x cubed y squared times 10 plus x to the 4th with a minus times y times 5 plus x to the 5th. So it's quite complicated, but using the binomial theorem is certainly much faster than trying to expand it by hand. Looking at another application of this You might not necessarily be asked to expand an entire binomial on the CLEP. You may simply be asked to find a given term of a very large degree binomial. So here I'm asking you for the 13th term of a plus b to the 27th, right? So what is this? Well, I know that this may be written as follows. K equals 0, 27. 27, choose k. A to the k, b to the 27 minus k. So I'll just plug in k equals 13 to get the 13th term. Or rather, I guess k equals 12, 13th term. So 27, choose 12. A to the 12 times b to the 27 minus 12. So I would get this. Now, of course, this is, perhaps not satisfying in that, this is some large number that we will not compute. You would need a calculator. But if we did have access to technology, we could easily compute this. This is something a computer is very good at. It's calculating things like factorial coefficients. So this is another thing you should be aware of for the CLEP is how to apply the binomial theorem to extract a particular term of a given binomial.